This evening, the office doesn't quite feel like itself. The paperclips in their dish suddenly look suspicious to me, the metal lamp on my desk a little too ready to leap, as if some invisible hand were testing its grip on every bit of iron in the room. I sit with my coat still on, hat tilted low, picturing this quiet space if something with an impossible magnetic field drifted too close. Filing cabinets ripped from the floor, desk drawers flung open, chair bolts torn free and pinned to the walls like iron filings in a school experiment gone wrong. Out here, the blinds only sway gently in the night air, and the only thing pulling on the room is gravity and a long day. But the folder in front of me says Magnetars in calm block letters, and it's enough to make every metal object feel like it's thinking about moving. Why, hello there. Good to see you tonight. If we haven't met yet, I'm Madeline Rowe, an astrophysicist turned private eye, trading telescope time for case files and quiet late-night physics. Tonight's investigation is a slow one, filed under collapsed stars and impossible magnetic fields, under objects so intense they can crack their own crusts just by shifting their thoughts around. So settle in, let the room blur a little at the edges, and we'll open the folder on Magnetars together, carefully, gently, one sleepy page at a time. One more thing, before we get completely lost in cracked crusts and quiet flares, if this kind of slow, deep space storytelling helps you unwind, you're very welcome to subscribe. It just means the next case file will be waiting for you whenever you need something calm and star-filled to fall asleep to. Okay, now let's get pulled into the story. Tonight, we're opening a case file on some of the most extreme stars the universe knows how to make, and we're going to handle them as gently as possible. Far out in our galaxy, there are tiny, collapsed stars with magnetic fields so strong they can crack their own crusts and light up the sky in X-rays and soft gamma rays. On paper, they sound violent. But here, for the next hour or so, they're just distant characters in a very slow, very quiet story. These objects are called Magnetars, neutron stars only about the size of a city, but wrapped in magnetic fields trillions of times stronger than the one you are sitting in right now. They spin, they glow, and they occasionally have outbursts. But they are unimaginably far away, and tonight they are just background scenery for you to fall asleep to. No quizzes, no equations, nothing you have to remember in the morning. Just a calm walk through some very strange astrophysics at a pace your mind can drift along with. For now though, you don't need to do anything at all. You can let your eyes grow heavy, let your shoulders sink a little deeper into the pillow, and just listen as we file Magnetars into the quiet cosmic background noise section of your brain. If you fall asleep halfway through the story, that's perfect. The stars will keep spinning without you. Every Magnetar story starts out fairly normally, at least by stellar standards. Imagine a massive star, 10 to maybe 25 times the mass of our sun. It burns hot and bright, racing through its nuclear fuel in just a few million years, a blink compared to the sun's lifetime. Deep in its core, the star is juggling heavier and heavier elements, building up an iron heart it cannot support forever. When that iron core gets too heavy, gravity wins. The core collapses in on itself in a fraction of a second, protons and electrons crushed together into neutrons. The outer layers of the star are thrown outward in a supernova, a huge explosion that briefly outshines the entire host galaxy. What is left behind is something much smaller and much stranger, a neutron star about 20 kilometers across, but crammed with more mass than the Sun. A neutron star is a kind of cosmic paradox. It is tiny, but incredibly massive. Solid, but with densities that push nuclear physics to its limits. 1 teaspoon of neutron star material would outweigh a mountain. And on top of all that, it carries a magnetic field, a leftover imprint of the original star's magnetism, amplified and squeezed by collapse. Most of the time, that field is strong but not outrageous, and those neutron stars show up as radio pulsars, sweeping beams of radio waves through space like cosmic lighthouses. Magnetars are the odd ones out. They are neutron stars whose magnetic fields didn't stop at strong. They went to extreme, into the range of 10 trillion to 1,000 trillion times Earth's magnetic field. In these stars, it is not rotation or accretion from a companion that powers most of their emission. It is the slow, restless decay of that enormous magnetic field. The field heats the star, twists the space around it, and sometimes cracks the crust in brief, violent fits of activity. So, how does a star end up with a magnetic field that strong? The leading idea goes back to the newborn moments of the neutron star's life. Right after core collapse, you have a hot, fluid object, still settling, still ringing from the violence of the explosion. It is rotating quickly, maybe dozens or even hundreds of times per second, and the interior is roiling with convection, hot material rising and cooler material sinking. In that environment, something like a gigantic dynamo can switch on. You can picture it roughly like this. Different layers of the star rotate at slightly different speeds, stretching and winding any seed magnetic field into tighter and tighter loops. Turbulent motions twist and fold those fields on smaller scales. The combination of rotation and fluid motion, a kind of alpha-omega dynamo in the technical language, can boost a modest field up to magnetar levels if the conditions are just right. Not every neutron star goes down this path. If the star is born spinning a bit more slowly, or if the convection dies down too quickly, the dynamo may never reach those record-breaking field strengths. Those stars become ordinary pulsars or X-ray sources. But in the subset that do cross that threshold, the result is a neutron star wrapped in an exceptionally strong, tangled magnetic field that will dominate its life story. Early on, that field also drains rotational energy. A very strong magnetic dipole behaves like a brake. It throws out electromagnetic radiation and winds, invisible relativistic sprays of particles that carry away angular momentum. So a magnetar is probably born spinning very fast, but it spins down quickly, slowing to a few rotations per second in a relatively short time. That is why many magnetars we see today have spin periods of a few seconds, rather than milliseconds. Inside the star, the magnetic field does not just sit there. It threads a super-dense interior, possibly containing superfluid neutrons and superconducting protons. The field can be organized in multiple components, some orderly and dipolar, others tangled and toroidal, wrapped around the star like invisible belts. Over thousands of years, those internal fields evolve, pushing on the solid crust above them. That slow, relentless shifting is what loads the system with stress. If you could look at a magnetar on an ordinary night with no flares and no bursts, it would not seem particularly dramatic at first glance. To our eyes, it would be invisible, just a pinprick of light lost in the darkness. But in X-rays, it glows steadily. Even in its quieter phases, a magnetar emits a persistent X-ray luminosity that is higher than we would expect from a normal cooling neutron star. Something extra is heating it from the inside. That something is the decaying magnetic field. As the field rearranges and relaxes, it dissipates energy as heat, warming the crust, and in some cases, small patches of the surface. Observationally, that shows up as a soft thermal component in the X-ray spectrum, a hot surface or one or more hotspots, with temperatures around a few million degrees. On top of that, there is often a harder tail extending to higher X-ray energies. One of the most useful pictures for explaining these spectra is the idea of a twisted magnetosphere. In a simple neutron star, the external magnetic field might look roughly like a bar magnet. Field lines emerging from one pole, looping out into space and returning at the other. In a magnetar, internal motions can twist those field lines, adding a toroidal component, something like taking a neat bundle of wires and giving it a firm twist. Twisting the field lines is not free. It requires electric currents flowing through the magnetosphere. Charged particles, electrons and positrons stream along the magnetic field, forming a kind of glowing halo of tenuous plasma around the star. When X-ray photons from the hot surface travel through this environment, they can scatter off those particles, especially at specific resonant energies tied to the magnetic field strength. This resonant cyclotron scattering reshapes the spectrum and helps produce the harder X-ray tail we observe. In more intuitive terms, you can imagine the magnetar surrounded by an invisible, twisted cage of magnetic lines threaded with currents. Light from the star's surface shines up into this cage and is bounced around, gaining and losing energy before eventually escaping to space. As the star rotates, once every 2, 5, or 10 seconds, those hotspots and scattering regions sweep past our line of sight, making the X-ray brightness rise and fall in a gentle pulse. That is how we measure the spin period and track its gradual slowing. Most of the time, this persistent emission is fairly stable. But magnetars are moody. They can undergo episodes where the X-ray flux rises, their spectra harden, and their pulse shapes change, a sign that the magnetosphere has become more twisted, or that new hotspots have appeared on the surface. These episodes blur into what we call outbursts, times when a usually faint magnetar becomes dramatically brighter and then slowly relaxes back to quiescence. In some magnetars, we have watched entire outbursts unfold from beginning to end. A source that was barely detectable in X-rays suddenly brightens by a factor of 10 or 100 or more. When we model the emission, we often find that the apparent emitting area on the surface has changed. It is as if a small patch, perhaps a kilometre across, on a star only 20 kilometres wide, has been heated intensely. Over weeks and months, that hot region cools and shrinks. The spectrum softens, the total flux declines, and the pulse profile often evolves in step. This kind of behaviour is exactly what you would expect if something, a local rearrangement of the magnetic field, or a fracture in the crust, suddenly dumped energy into a small part of the star's outer layers. The crust conducts that heat sideways and inward, and the magnetosphere gradually untwists. These outbursts are one of our best clues to what is going on under the surface. They tell us that the crust is not just a passive shell, it is an active participant in the story, bearing the stresses of the interior field, occasionally yielding, and then taking time to recover. They also tell us that the magnetosphere can store and release energy in a more continuous way than the most dramatic bursts would suggest. If all of this sounds like a lot to hold in your head, you don't need to. You can let the details blur at the edges. All you really need, as you lie here, is the picture of a tiny star slowly healing from a magnetic strain, its hot patches shrinking, its glow fading back to a steady, quiet X-ray hum. Somewhere far away, telescopes keep watch on that slow cooling. Here, you are just borrowing the story as a backdrop while you fall asleep. Of course, magnetars are best known not for their quiet phases, but for their sudden outbursts of energy. Astronomers group this activity roughly into 3 categories: short bursts, intermediate flares, and the rare, spectacular giant flares. Short bursts are, well, short. They typically last a fraction of a second to about a second. In that instant, the magnetar releases a huge amount of energy in X-rays and soft gamma rays. If you plotted the brightness over time, you would see a spike that rises quickly and then falls away, sometimes with a bit of structure as the emission tapers off. These bursts can come in swarms, dozens or hundreds, in a single active episode, like a storm of tiny magnetic hiccups. Intermediate flares last longer, seconds to tens of seconds, and carry more energy. Their light curves often show a more complex rise and decay, sometimes with pulsations at the star's spin period superimposed. They are still small compared to a supernova, but enormous compared to anything we are used to on Earth. Then there are the giant flares. Only a handful have ever been seen in our galaxy and its satellites. In a giant flare, a magnetar can release as much energy in a few tenths of a second as the sun emits in hundreds or thousands of years. The flare starts with an incredibly bright, sharp spike, followed by a tail that can last several minutes, during which the X-ray brightness rises and falls in time with the magnetar's spin. Embedded in that tail, careful analysis has revealed faint quasi-periodic oscillations, subtle ringing at specific frequencies. These may be the natural vibration modes of the neutron star itself, excited when the flare's violence shakes the crust and couples into the interior. In a sense, giant flares turn magnetars into bells, and by listening to their ringing, we can learn about their internal structure. What triggers all this activity? The honest answer is that we have a set of closely related ideas rather than one final picture. One family of models emphasizes crustal fractures. As the internal magnetic field evolves, it stresses the solid crust until it cracks or yields. Those sudden shifts can send shear waves rumbling through the star and twist the external field lines, launching waves into the magnetosphere. Charged particles are accelerated, photons are produced and reprocessed, and for a brief moment, the magnetar blazes. Another family of ideas leans more on magnetospheric instabilities. If the external field becomes too twisted, it can suddenly reconnect, somewhat like a solar flare, but in far more extreme conditions. Magnetic energy stored in those twisted loops is converted rapidly into particle acceleration and radiation. The crust may still be involved because anchored field lines mean anchored stresses. But the key event in this view is the sudden topological change in the magnetosphere. It is likely that both ingredients matter. The interior field builds stress. The crust resists, then yields. The magnetosphere responds with a bright, short-lived emission episode. From our perspective far away, all of that drama is just a spike in a detector's count rate, a blip on a screen, a few seconds of data to file away. For you, curled up in bed, it can be filed under harmless cosmic fireworks, interesting to think about for a moment, and then easy to let go. For a long time, magnetars were thought to be radio silent. We saw them in X-rays and gamma rays, but repeated searches for pulsed radio emission turned up nothing. Then, to everyone's surprise, a few magnetars suddenly lit up at radio wavelengths. Sources like XTEJ1810-197 began to produce bright, highly variable radio pulses, often in the aftermath of an X-ray outburst. These radiomagnetars do not behave exactly like ordinary radio pulsars. Their radio spectra tend to be flatter, their pulse shapes can change rapidly, and the emission can switch on and off over months to years. When we compare their overall energy budgets, an interesting pattern emerges. In the radio loud phase, their rotational energy loss rate, the power available from spinning down, is actually larger than their X-ray luminosity. In other words, at those times, rotation could plausibly support the radio emission, even if the X-rays remain magnetically powered. This suggests that whether a magnetar is radio loud or radio quiet may depend on its detailed field configuration and particle environment at a given moment. Strong, twisted magnetospheres filled with dense plasma might quench the radio beam or scatter it away. Simpler, less loaded configurations might let radio waves escape along open field lines, much as they do in ordinary pulsars. There are also neutron stars that, by usual measures, do not look like magnetars at all, at least not on the surface. Their spin-down inferred dipole fields are relatively modest, below some traditional magnetar threshold, and yet they show bursts, outbursts, and other hallmarks of magnetar activity. These so-called low-B magnetars tell us that the dipole field we infer from spin-down is only part of the story. Strong internal fields and higher-order multipoles near the surface can still be present, even if the large-scale dipole has decayed. That means magnetar-like behavior might be more widespread than we first thought, hiding in objects we originally classified as ordinary. The neat lines between categories, magnetar, pulsar, X-ray source, start to blur. Instead, we see a continuum of neutron stars with different magnetic personalities at different times. When you zoom out, magnetars become one branch on a larger family tree. Massive stars die. Some leave behind black holes. Some leave neutron stars. Among those neutron stars, some shine mostly in radio, some in X-rays, some accrete from companions, some drift quietly, and a subset are pushed into this magnetar regime where magnetic fields dominate their evolution. Over tens of thousands of years, a magnetar's magnetic field will gradually relax. Its bursts will become rarer. Its persistent emission will fade. It may eventually come to resemble a more typical neutron star, its most violent youth behind it. Or it might remain restless for a long time, continuing to crack and flare sporadically. The details depend on the internal field configuration, the crust's properties, and the environment it lives in, things we are still working to understand. For tonight, you don't need to follow all of those forks in the road. You can just keep the simplest version in your mind. A big star collapses. It leaves a tiny, dense remnant. And if the conditions line up, that remnant becomes threaded with an enormous magnetic field that slowly, quietly spends itself over thousands of years. You can imagine the magnetar as a little ticking clock in the dark, turning once every few seconds, surrounded by its invisible cage of magnetic lines. Every so often, the cage shifts, the crust complains, and a bit of stored energy is released. Most of the time, though, it just glows softly in X-rays we cannot see. While galaxies spin, stars are born and die, and the universe continues its slow work. Here, in your room, things are much simpler. You have the rise and fall of your breath, the gentle weight of the blankets. The way sounds grow a little softer as your mind starts to let go of the day. If numbers and technical terms from earlier in the episode are still drifting around, you can let them dissolve now. They don't need to be filed neatly. They can just fade, like after images when you close your eyes. Somewhere far away, a magnetar rotates once, twice, 3 times, silently marking out the seconds. Here, time can stretch a little. You can let your jaw unclench, let your hands relax, let your thoughts slow. The universe will keep its own complicated rhythms. You only need to keep one, in and out, over and over, a quiet pulse of your own. If sleep is already starting to take over, you can let it. You don't need to stay for the credits. Magnetars will go on being magnetars, tiny, over-magnetized remnants in a large, indifferent cosmos. And I'll be here whenever you want another slow case file to drift off to. If you are still awake and comfortable, we can quietly leaf through a few individual case files, specific magnetars that have made their presence known in our data. You don't need to memorize the names. They can wash over you like street names in a city you are just passing through. The first file belongs to a source, often referred to as SGR 1806-20. The name is just its coordinates on the sky, a label that tells astronomers where to point their instruments. It lives in a crowded region of the Milky Way, buried behind thick clouds of gas and dust, invisible in optical light, but bright in high energy bands. For years, it was known as a soft gamma repeater, one of a handful of objects that produce repeated bursts of soft gamma rays. On an ordinary day, SGR 1806-20 glows steadily in X-rays. Every now and then, it emits short bursts, little flashes that last less than a second. Then, in December of 2004, it produced something extraordinary, a giant flare. Spacecraft across the solar system, including some not even aimed at it, registered a huge spike in gamma rays. For a fraction of a second, this tiny object briefly outshone most of the galaxy. After the initial spike, the brightness decayed, modulated by the star's rotation. The giant flare left an imprint not just on detectors, but on theoretical work, pushing models of magnetar energy release to their limits. And yet, from our vantage point in a dark room, it can just be one more distant thunderclap in the story, a reminder that even small objects can be intense without posing any threat to us at all. Another folder is labelled SGR 1900+14. Like 1806-20, it is a soft gamma repeater. In August of 1998, it too produced a powerful flare, though somewhat less energetic than the 2004 event. Observations of its activity, both before and after the flare, helped solidify the connection between these repeating gamma ray sources and strongly magnetized neutron stars. Over time, monitoring SGR 1900+14 has revealed how magnetars can change their pulse shapes and spectral properties as their magnetic configurations evolve. There is a slightly different flavour of case in the folder for XTEJ 1810-197. This object was first identified as an X-ray source during an outburst. It brightened dramatically, and then slowly faded over months and years, exactly the kind of transient magnetar behaviour we talked about earlier. What made it especially interesting is what happened afterwards. It became one of the first magnetars observed to emit pulsed radio waves. For a time, XTEJ 1810-197 was a loud, erratic radio pulsar. Its pulses changed shape from observation to observation. Its flux varied, and then, eventually, the radio emission faded again. Watching this source switch its radio personality on and off offered a rare window into how magnetar magnetospheres can reorganize themselves after an outburst. You could spend an entire night paging through these individual files. Each magnetar has its own quirks, slightly different spin period, slightly different flux history, bursts that cluster in time or arrive singly, quiet intervals, and active spells. The overall pattern is the same. A tiny, dense star dominated by its magnetic field, but the details rhyme rather than repeat exactly. For you, lying here, they can all be folded into a single composite image, a handful of small, invisible stars scattered around the galaxy, each with its own rhythm, each occasionally jolting into a flare, most of the time tick-ticking softly in X-rays. You don't need to keep the names straight. You can let them blur together into a soft background of "this has all been observed," and then let that too fade into the dark. One of the calming things, at least to me, is remembering just how indirect our contact with magnetars really is. We never get close. We never send probes. All we have are tiny variations in the light they send us, picked up by instruments orbiting far above the Earth. High-energy telescopes don't look much like the classic glass lens observatories you might imagine on a mountaintop. To catch X-rays and gamma rays, we use detectors in space, satellites with coded masks and scintillators and silicon arrays, more like carefully shielded particle counters than traditional cameras. They sit above the atmosphere because our air does a very good job of blocking these high-energy photons. When a magnetar is quiet, its persistent X-ray emission might show up as a faint, steady signal. Astronomers watch how that signal rises and falls as the star rotates, building up a pulse profile. They measure the spectrum, how many photons arrive at each energy, and see how it changes over time. The details of that slow, steady glow give clues to the surface temperature, the presence of hotspots, and the structure of the magnetosphere. During a burst or flare, the data look very different. Suddenly, the count rate jumps. Detectors that register only a few photons per second may suddenly record thousands. Onboard software flags these jumps, triggers special data modes, and alerts ground-based teams. In a matter of seconds, the instruments have seen the entire flare from rise to fall, storing the timing and energy information needed to pick it apart later. On Earth, those data are downloaded, calibrated, and turned into light curves and spectra, plots of brightness versus time and energy versus intensity. Most of the work is quiet and methodical, subtracting background noise, correcting for instrumental effects, and cross-checking with other telescopes. The wow moments, the giant flare spikes, are rare. Much of magnetar astronomy is careful watching, punctuated by brief, intense events. Radio observations add another layer. Large radio dishes or arrays of smaller antennas stare at a patch of sky. If a magnetar happens to be in a radio loud phase, its pulses show up as small periodic increases in the received signal. By folding the data at the known spin period, astronomers can build a picture of the average radio pulse shape and track how it evolves. When the radio emission switches off again, the telescopes see nothing, just the usual hiss of the universe. In the future, new instruments will add more dimensions. X-ray polarimeters will not just measure how bright a magnetar is at different energies, but also how the electric field of the light is oriented. That information can reveal subtle effects predicted by quantum electrodynamics in ultra-strong fields, like the vacuum itself acting as a strange lens. Timing missions with larger collecting areas can catch fainter oscillations and more subtle variations in pulse profiles. From your perspective, all of that can shrink down to something very simple. Somewhere, an orbiting detector registers a few more counts per second. A line on a graph wiggles. Someone, at some point, notices the wiggle, compares it to past ones, and adds a note to the Magnetars file. The universe hums along, and you, here, can use that hum as a soft, distant sound to fall asleep to. If you are still with me, we can turn the case file on its side and look inside a magnetar for a while. Not just at the bursts and the flares, but at the quiet structure that makes them possible. We are going to move slowly here, layer by layer, like peeling back the shells of a very dense, very strange onion. You don't need to remember the terms. You can just let each layer pass by and fade as we move inward. Start at the surface. A magnetar's outermost skin is extremely thin by everyday standards. If the star is about 20 kilometers across, the solid crust might be only about a kilometer or so deep. The very top is a thin atmosphere, maybe just a few centimeters of light elements like hydrogen or helium, or a more complex mix depending on the star's history. That atmosphere is where the X-ray photons we see finally escape into space. Just beneath that is the outer crust, a lattice of atomic nuclei packed together so tightly that their electrons are no longer bound to individual atoms. Instead, the electrons form a highly degenerate sea, a sort of quantum fluid holding everything together. Gravity is unimaginably strong, pressing this lattice into a rigid crystalline structure. You can imagine it as an ultra-dense metallic layer, though the densities and pressures are far beyond anything we would call metallic in ordinary materials. Deeper down, in the inner crust, nuclei become more and more neutron-rich. Some neutrons begin to drip out and form a superfluid, threading through the lattice. The matter here is a hybrid, solid, and liquid at the same time, with nuclei arranged in patterns that can take on exotic shapes, spheres, rods, slabs, the nuclear pasta phases people like to talk about. It is a place where nuclear physics and condensed matter physics overlap in strange ways. Below the crust lies the core. Here, densities exceed that of ordinary atomic nuclei. Neutrons dominate, forming a superfluid that can flow with almost no resistance. A fraction of the particles are protons and electrons, and the protons are expected to form a superconducting phase. In a superconducting core, magnetic field lines do not just wander freely. They are bundled into thin flux tubes that thread the fluid like invisible strings. In this environment, the magnetic field is not just a static background. It is woven into the structure of the matter itself. The way the field evolves, how it moves, how it decays, and how it couples the core to the crust depends on how these flux tubes and superfluid vortices interact. It is a rich, complicated problem that sits at the intersection of quantum mechanics, nuclear physics, and magnetohydrodynamics. In the crust, the field evolution is often described in terms of two main processes: ohmic dissipation and Hall drift. Ohmic dissipation is the simple one. Currents flowing through the crust encounter finite electrical resistance, and over time, that resistance dissipates magnetic energy as heat. Hall drift is more subtle, describing how the field is advected and rearranged by the currents themselves without necessarily changing its total energy. Together, these processes can move magnetic flux around, concentrating it in certain regions, twisting it, or letting it slowly unwind. Deeper in the core, another process called ambipolar diffusion can become important. In simple terms, it describes how the charged and neutral components of the fluid move relative to each other, dragging the magnetic field along. In the dense, superfluid, superconducting interior of a magnetar, ambipolar diffusion can redistribute magnetic energy over very long timescales, thousands to millions of years. It is a slow, persistent way of reshaping the field from within. All of these processes, Hall drift in the crust, ambipolar diffusion in the core, ohmic decay everywhere, act on different timescales. Some rearrangements are gradual, like tectonic plates creeping. Others can push localized regions of the crust toward instability, priming them to slip suddenly. The steady evolution of the field builds up stresses. When a threshold is crossed, the crust can fracture or yield plastically, and energy is released in a burst or outburst. You can think of the magnetar's interior as a slow-motion machine. Deep inside, magnetic flux tubes shuffle and drift, guided by microscopic forces you don't need to visualize. The crust above them is strong but not unbreakable, absorbing those stresses over centuries and then, occasionally, letting go. The magnetosphere outside is the responsive shell, twisting as the internal field evolves and snapping when too much twist accumulates. Observationally, we mostly see the outermost consequences of this deep activity. We see the persistent X-ray light, powered by the heat that leaks out as magnetic energy is dissipated. We see the gradual changes in the spin-down rate, reflecting how the large-scale magnetic dipole evolves. We see bursts and flares when parts of the structure cannot hold on any longer and rearrange suddenly. The interior, with all its superfluid and superconducting subtleties, remains hidden behind the crust. Over the lifetime of a magnetar, this internal evolution can change its personality. In its youth, the internal field might be tangled and strong, leading to frequent, powerful activity. As time passes, some components of the field decay or reconfigure, and the star may settle into a quieter phase with fewer bursts and lower persistent luminosity. Eventually, it may look, from the outside, much like an ordinary neutron star, even if traces of its magnetar past remain imprinted in its interior. Lying here, you don't have to picture every detail of that hidden machinery. It can be enough to imagine that under the smooth, glowing surface of a magnetar, there is a layered structure, a thin, rigid crust, a deep fluid core, and a magnetic field permeating all of it, slowly shifting, slowly relaxing. Occasionally, those slow changes reach the surface in the form of a flare. Most of the time, they simply contribute to a steady, quiet warmth. If your mind is starting to wander, you can let it. Let the words superfluid and flux tube become soft and blurry. Let the images of lattices and layers fade. You are not trying to reconstruct a physics diagram in your head. You are just letting the idea settle, that even in something as fierce as a magnetar, there is a deep, slow interior life unfolding on timescales far longer than a human lifetime. Somewhere, as you listen, a magnetar's crust is cooling slightly. Its internal field is drifting by a microscopic amount. Its spin period is lengthening by a tiny fraction of a second per year. None of that demands anything from you. You are allowed to be still and to let your own interior processes, your heart, your breath, your slow transition towards sleep, take center stage instead. We have spent a lot of time right up close to a single magnetar in our imagination, hovering over its surface and peering into its interior. To finish filling out the file, it can be soothing to zoom back out and see where these objects fit in the wider galaxy, and maybe even beyond it. Think of this as pulling the camera slowly away, from the star to its surroundings to the larger structure around it. Magnetars are not scattered randomly. They tend to live in regions where massive stars were born not that long ago in cosmic terms. Many are found in or near the plane of the Milky Way, where gas and dust are densest and star formation is most active. Some are associated with supernova remnants, expanding shells of gas still glowing from the explosion that created the neutron star at their center. In a few cases, magnetars seem to belong to very massive star clusters, groups containing many hot, luminous, short-lived stars. These clusters are stellar nurseries for the kinds of progenitors that can eventually collapse into neutron stars or black holes. The presence of a magnetar in such an environment reinforces the idea that they come from some of the most massive stars that manage to leave neutron star remnants, rather than collapsing directly into black holes. Astronomers estimate a magnetar birth rate by combining several lines of evidence: how many magnetars we see today, how long they are likely to remain active in their current state, and how much of the galaxy we are effectively surveying. The details are fuzzy, but the broad picture suggests that magnetars are not extraordinarily rare. A reasonable fraction of neutron stars may pass through magnetar like phases, especially early in their lives. That ties back to the idea that magnetars are not a completely separate species, but a particular magnetic state that some neutron stars occupy. A newborn neutron star might begin with a strong field, behave as a magnetar for a few thousand or tens of thousands of years, and then, as its field evolves and decays, transition into something that looks more like an ordinary pulsar or a quieter X-ray source. From a human perspective, these timescales are enormous. From the star's perspective, it is just one chapter in its long cooling history. Magnetars may also play roles in other cosmic phenomena that seem, at first glance, separate. For example, some models of gamma-ray bursts, those brief, intense flashes of high-energy radiation seen at cosmological distances, invoke newly formed, rapidly rotating, highly magnetized neutron stars as central engines. In these scenarios, a millisecond magnetar born in a core collapse event or a neutron star merger can power a collimated outflow that we observe as a burst. There are also connections to fast radio bursts, or FRBS, mysterious millisecond-long flashes of radio waves coming from far beyond our galaxy. In at least one case, a fast radio burst has been traced back to a known galactic magnetar during an active episode, strongly supporting the idea that at least some FRBs are produced by magnetars. In those models, magnetic reconnection events, or crustal failures, launch short, coherent radio pulses, sometimes accompanied by X-ray or gamma-ray counterparts. Not every fast radio burst has to come from a magnetar, and not every magnetar flare produces a fast radio burst. But the link highlights how these compact objects can sit at the crossroads of multiple transient phenomena. A single magnetar, with its strong, evolving field, has the potential to generate a range of signals: steady X-ray emission, bursts, flares, radio pulses, and perhaps, under the right circumstances, brief but brilliant radio flashes visible across cosmological distances. In our own galaxy, magnetars are relatively quiet neighbours. There are only a few dozen known, and they are all far away, thousands or tens of thousands of light years from Earth. Even when they produce giant flares, the effects here are limited to small, temporary changes in our upper atmosphere and brief spikes in space-based detectors. They are dramatic on their own terms, but distant enough that we experience them only as data. Still, they serve as important testbeds for physics under extreme conditions. By watching how magnetars behave, astronomers learn about the behaviour of matter at densities and field strengths far beyond what we can ever explore in a lab. Theories of nuclear structure, superconductivity, and strong field quantum electrodynamics are all nudged and shaped by what magnetars do. In that sense, these tiny stars help us refine our understanding of the fundamental laws that govern the universe. They also contribute, in a quieter way, to the ecology of the galaxy. The supernovae that give birth to magnetars enrich the interstellar medium with heavier elements. Their flares and winds inject energy into surrounding gas. Over millions of years, that gas can cool, collapse, and form new generations of stars and planets. The cycle of birth, death, and recycling continues, with magnetars as one of many actors on a large stage. If you zoom even further out, to the scale of many galaxies, magnetars become part of the story of cosmic magnetism. Galaxies have their own large-scale magnetic fields, shaped by turbulence, rotation, and feedback from stars and black holes. The existence of strongly magnetized neutron stars tells us that stellar evolution is an important way of concentrating and reorganizing magnetic energy on smaller scales. That, in turn, feeds back into how we think about the origin and amplification of fields on the largest scales. For now, though, you don't need to hold the whole universe in your head. You can shrink things back down to something simple. Somewhere in the Milky Way, in a region full of gas and dust, where stars formed not long ago, a magnetar orbits quietly. It is one small remnant among many. Most of the time, it does nothing that would stand out to human senses. Occasionally, it flares, and distant instruments notice. Then it goes back to its slow spin, its slow cooling, its slow magnetic evolution. You are here, on a planet warmed by an ordinary star, listening to a story about these extremes. The contrast can be oddly comforting. All the violence and intensity of magnetars is, from your vantage point, completely abstract. The only thing you feel directly is your own body easing into rest, the way the bed supports you, the way your breathing settles into a rhythm, the way your thoughts get a little softer at the edges. There is one more layer to magnetars that is worth brushing against on our way out, even if we don't hold onto the details. Their magnetic fields are so strong that they push light and matter into regimes we cannot reproduce in any laboratory on Earth. In these fields, quantum electrodynamics, the theory of how light and charged particles interact, starts to behave in ways that feel a little exotic. One example is something called vacuum polarization. In everyday life, we treat empty space as empty. But in quantum field theory, the vacuum is a seething medium of virtual particles that can briefly appear and disappear. In extremely strong magnetic fields, that medium can respond differently to different polarizations of light, acting like a kind of crystal. Light with one polarization direction may travel slightly differently than light with another. Around a magnetar, this means that as X-ray photons travel outward through the strong field, their polarization states can evolve. The result is that the emerging radiation can carry a distinct polarization signature, one that encodes both the magnetic field geometry and these subtle quantum effects. Measuring that signature is difficult but not impossible, and it is one of the reasons future X-ray polarimetry missions are so exciting to people who study strong field physics. Magnetars may also, in certain configurations, emit gravitational waves. If their internal magnetic fields deform them slightly away from perfect symmetry, then as they spin, they can radiate a faint, continuous gravitational wave signal. Starquakes and flares, too, might excite oscillation modes that send out brief ripples in space-time. Detecting such signals is extremely challenging, but even upper limits tell us something about how distorted a magnetar can be. Multi-messenger astronomy, combining electromagnetic observations with gravitational waves and perhaps neutrinos, may eventually bring magnetars into sharp focus as laboratories for fundamental physics. For now, though, you can just tuck away the idea that these tiny stars touch laws of nature at their edges, pressing on the boundaries of what we can test. They are like natural experiments running far away under conditions we can only model. As we wind down, it might help to gently recap the story in simpler terms, letting any sharp edges fall away. You can think of it as a very slow, very soft summary, meant more to lull than to teach. First, there was a massive star. It burned hot and fast, living a short, brilliant life. When its core ran out of fuel it could use to support itself, the core collapsed, and the outer layers were blasted outward in a supernova. What remained was a neutron star, tiny, dense, and spinning quickly. In some of these newborn neutron stars, conditions were just right for a powerful dynamo to switch on. Convection and rapid rotation wound up the magnetic field, amplifying it to enormous strengths. Those stars became magnetars, neutron stars, where magnetic energy, not just rotation or accretion, powers much of what we see. Over time, the magnetic field evolves. It heats the star from within, creating hotspots on the surface that glow in X-rays. It twists the magnetosphere, filling it with currents and particles that reshape the emerging light. Most days, the magnetar emits a steady, pulsed X-ray glow, turning once every few seconds like a small, distant heartbeat. Sometimes, though, the stresses become too much. The crust yields, or the magnetic field in the magnetosphere suddenly rearranges. Energy is released in a rush. Short bursts flicker, intermediate flares surge, and very rarely, giant flares roar for a few seconds and then fade. From our point of view, it is all just a pattern of counts in a detector, a little storm of high-energy photons from far away. A few magnetars surprise us by speaking in radio as well as in X-rays. A few hide their magnetic strength beneath modest dipole fields, behaving like magnetars on the inside while looking ordinary on the outside. All of them together make up a spectrum of behaviors, a reminder that nature does not always draw hard lines between categories. And in the background of all that, the universe just keeps going. Stars form, shine, and die. Galaxies drift and collide. Black holes merge. Planets spin quietly around their suns. On one of those planets, in a small room, you lie listening to this, feeling your own body grow heavier and softer with each breath. You don't need to hold on to any of the technical words: neutron star, magnetosphere, soft gamma repeater. They can all fade like chalk on a blackboard in the rain. What you can keep, if you like, is just the feeling that the universe is vast, complex, and very far away, and that you are allowed, in this moment, to be small and still and sleepy inside it. Let your attention drift away from the stars now and back to your body. Notice the way the mattress supports you. Notice the way your breath moves in your chest without you having to ask it to. Thoughts may still wander in and out, and that is fine. You can let them pass like distant bursts from a magnetar, brief, bright, and gone. The baseline underneath is quiet. If your eyes are heavy, let them stay closed. If your jaw is tight, loosen it just a little. If your hands are clenched, unfurl them. Somewhere far away, extreme stars are cracking and cooling, fields are evolving, and data are being collected. Here, you are doing the opposite, unwinding, cooling down, letting the field of your day finally decay into rest. When sleep comes, whether it is in the next minute or a few pages from now, you can let it have you. I'll keep the file open a little longer, just in case, but you don't need to listen anymore. You can, gently and quietly, fall asleep.